Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcomes H and I from the topic of chemical bonding from the JCH2 chemistry syllabus. Learning outcomes H, candidates should be able to describe the following forces of attraction, electrostatic in nature, intermolecular forces based on permanent and induced dipoles, such as in CHCl3, Br2, and the liquid noble gases, as well as hydrogen bonding using ammonia and water as examples of molecules containing the NH and OH groups. Learning outcomes I, to be able to outline the importance of hydrogen bonding to the physical properties of substances, including ice and water. Okay, so what are intermolecular forces? Intermolecular forces are the attractive forces which keep solids and liquids together, as well as repulsive forces between molecules. So the word intermolecular, right? Basically the word inter, it's between, and then of course molecule just means molecule. So it's basically forces between molecules. And why are we interested in studying intermolecular forces of attraction usually? Is because as the strength of the intermolecular forces increases, more energy will be required to break these forces and to separate the molecules so that we can turn the molecule from a solid state into a liquid state, and also to turn the compound from a liquid state to a gaseous state. And if the strength of the intermolecular forces is stronger, then more energy will be required to break the stronger attraction between the molecules, and this will result in a higher melting or boiling point. So the main reason that we're interested in studying intermolecular forces of attraction is because if we are able to determine the type of intermolecular forces of attraction a molecule has, and basically the strength of that type of intermolecular forces of attraction, then we will be able to judge whether that molecule has a high or low melting or boiling point. So it's basically to predict the melting and boiling point because it's closely related to that. Okay, so how many types of intermolecular forces of attraction are there? There are mainly four main types. So increasing orders of strength. So the induced dipole forces is the weakest. And then like the second weakest would be the permanent dipole induced dipole forces, followed by the permanent dipole forces. And then the final strongest intermolecular forces of attraction would be the hydrogen bond. So we will be going through each and every one of these in a bit of greater detail to explain what do they actually mean. Okay, so the first type of intermolecular forces of attraction is induced dipole forces. So for a non-polar molecule, the electron distribution is on average evenly distributed. So let me do a quick refresher on how do we decide whether a molecule is polar or non-polar. So first we have to draw the shape of the molecule using the VSEPR theory. So for example, if we have such a molecule, like for example this, CH3F. So because it has 4 electron domains around carbon, so the general shape is actually that of tetrahedral. And what you would do is you would draw an arrow towards the more electronegative element along the bond, and you add up all the bond dipoles. In this molecule, there's only one bond dipole because for all purposes of deducing bond polarity, we would say that carbon and hydrogen has very close electronegativity. So there's no difference in electronegativity between carbon and hydrogen, such that we do not draw an arrow towards the more electronegative element between carbon and hydrogen. Since there is only one polar bond in this molecule and the arrow points towards fluorine, since fluorine is more electronegative than carbon, in fact, fluorine is the most electronegative element in the entire periodic table, this molecule, when you add up all the bond dipoles, which is only one bond dipole, there will be a net dipole moment, and hence the overall molecule has a net dipole moment, and this molecule is a polar molecule. Okay. On the other hand, if I look at another molecule such as CF4, right? CF4 will look like this, and when I would draw a bond vector, I would draw along all the bonds, and there will actually be 4 of them. And if I add these 4 vectors up vectorially, I can show that they actually add up to the 0 vector, which means that this molecule is overall nonpolar. And when the molecule is nonpolar, what it means is that the electron density, the distribution of the electrons around this molecule, right, is on average evenly distributed. That means there's an equal chance of finding the electron in every part of the space around this molecule. Okay, so that is what this means. if the molecule is nonpolar, then the electron distribution is on average evenly distributed. There is no region of space whereby there is a greater density of electron as compared to another. Okay. However, right, because electrons are constantly in motion, so they're actually constantly moving, and by chance, there can be a greater amount of electrons that will congregate in one area of the molecule, and this will result in an induced dipole. So for example, if we look at a spherical shape, right, the electrons can be said to be on average evenly distributed. However, because they are constantly moving around, right, so what can happen is that imagine if all the 4 electrons will by chance happen to congregate on the left side, right, then there will actually be a net dipole because there will be a greater excess of electrons on the left hand side, and this will acquire a small partial negative charge. This delta means small, a small amount of negative charge, whereas like because here there is a net diffusion of electrons, so we can say that it actually gains a partial positive charge. And this will create an instantaneous dipole moment. Because there's a separation of charges, there's greater electron density on the left-hand side as compared to a lower electron density on the right-hand side. And this will be called an induced dipole moment in the otherwise nonpolar molecule, because it was originally nonpolar because the electrons are evenly distributed. By chance, electrons congregate on the left-hand side, so it creates an induced dipole in an otherwise nonpolar molecule. Okay, so this is the same picture that I draw. So for example, this molecule was evenly distributed, the electrons, but at any instant of time, the electrons congregate on the left-hand side, creating a net dipole moment, whereby there is a delta minus on the left and a delta plus on the right. Now, when this instantaneous dipole is created and it approaches another molecule, which is also nonpolar, whereby the electrons is evenly distributed, what would happen is that this instantaneous dipole would induce a dipole in this. What it means is that it will cause this molecule to rearrange the electron configuration such that it actually creates a situation whereby there is more electrons on this side, creating a delta minus, and less electron density on this side, thus creating a delta plus. And since there is attraction between plus and minuses, right, there will be some attraction between this delta plus and this induced delta minus on this side, and there will be attraction between these two molecules. And hence, this dipole is an instantaneous dipole created by the random fluctuation of the electron density, and this is an induced dipole because it's caused by this instantaneous dipole. So this is also another term for it. This is also called an instantaneous dipole, induced dipole interaction. So I like to say that this is the weakest type of intermolecular forces of attraction because this instantaneous dipole is created by chance, and this induced dipole is created by this dipole that happened by chance. And remember the electrostatic forces of attraction, right? So the electrostatic force is proportional to Q1, Q2 over R1 plus R2, okay? Which is basically like it's proportional to the magnitude of the charge. And if these are delta plus and delta minus, it's only a partial positive charge and partial negative charge. And it's also created by chance. Hence, the instantaneous dipole induced dipole forces of attraction is the weakest among the 4 types of intermolecular forces of attraction. So it's, in other words, right, it's also right to say that basically if a molecule, the intermolecular force of attraction is the ID forces of attraction. So like the abbreviation for this is ID. So ID force of attraction, then it will be the weakest, and the melting point and boiling point will be expected to be the lowest because the least amount of energy is required to break this force of attraction. Okay, so what are the factors that can decide on how strong these ID forces of attraction are? So in general, they are actually much weaker than ionic, covalent, and metallic bonds. So let's think about why this is so. For example, in an ionic compound, let's say like for Na plus and Cl minus, right? The electrostatic forces of attraction is between a 1 plus charge and a 1 minus charge. So the ID interactions, right, as we discussed just now, is between a partial plus and a partial minus charge, right? And of course, the magnitude of these charges is much smaller as compared to a full plus and full minus charge. And that's the reason why the ionic bond is much stronger than the molecules that have ID interactions. The covalent bond, on the other hand, is, for example, the electrostatic forces of attraction between the nucleus and the shared pair of electrons. So of course, electrons is like full minus charge, and the nucleus is also full plus charges. So the covalent bond, it's also much stronger than this because the magnitude of the charges that is involved in the electrostatic attraction is much larger than that in the ID-ID interactions. Metallic bonds, on the other hand, is the attraction between, like, let's say the Na plus in the sodium metal, between the Na plus and the C of delocalized electrons in the solid lattice. And hence, the magnitude of the charges is like 1 plus and 1 minus, and this is also much stronger in magnitude. The magnitude of the charges is also much higher than that in ID-ID interaction, and that's the reason why the ionic bond, the covalent bond, and the metallic bonds is much stronger than ID-ID interactions. They're actually much stronger than any of the intermolecular forces of attraction that we'll discuss in the later part of this lecture. Okay, so the strength of ID-ID interactions depend on the polarizability of the molecule as well as the shape of the molecule. So basically, if we have established that two molecules, molecule A and molecule B, both interact through ID-ID interactions, and we would like to decide which molecule has the stronger ID-ID interactions, then we would base the discussion on these two factors: how polarizable the molecule is, and what is the shape of the molecule. Okay, so basically the polarizability of the molecule basically means that if the mass of the molecule is larger, then generally the number of electrons will be larger. If the number of electrons is larger, right, then this effect will be stronger because you have a greater number of electrons that congregate on one side at any given amount of time. And hence, the delta minus created by a larger number of electrons congregating on one side will be stronger as compared to another molecule whereby there is a smaller number of electrons congregating on one side. Okay, so basically, if you have more electrons, the delta minus created by the congregation of a larger number of electrons on one side will be greater. And hence, the greater the mass of the molecule, the greater the number of electrons, and the stronger will be the induced dipole moments created in the molecules, and the stronger will be the ID-ID interactions between the molecules. So higher mass usually means more electrons, and it will mean stronger ID-ID interactions. Okay, so we can just look at the MR of the two molecules that is involved, that we're trying to compare, that both are ID-ID interactions. Okay, and on the other hand, also, if the size of the molecule is larger, then the electrons are also further away from the nucleus and they're actually more free to move about. And if they're more free to move about, then it's easier for the electrons to congregate on one side at any given moment of time. So basically, this will also mean that if the size of the molecule is larger, then the induced dipole moments will be larger and the stronger will be the ID-ID forces of interactions. The second factor is the shape of the molecule. So for example, right, if I were to look at this molecule, butane, okay, so like all this is hydrogens. Okay, so this clearly is a molecule whereby it interacts through ID-ID interactions because there's actually no polar bonds involved in this molecule. If we were to compare it to another molecule, which is say isobutane, okay, a branch isomer of butane, they have the exact same molecular mass. Okay, because like remember just now we mentioned that if a molecule has a greater molecular mass, it will have more electrons and the induced dipole created will be stronger, and hence the ID-ID interactions will be stronger. However, because these two are isomers, it will mean that they have the exact same molecular mass. So we cannot use molecular mass to decide which one has a stronger induced dipole interactions, and we cannot use that principle to figure out which one has a higher melting point or boiling point. Okay, however, in this molecule, it is long and unbranched, and the interaction between this molecule, right, and I'm just going to use a simplified drawing to represent another molecule. So like 1, 2, 3, 4. Okay, so this represents butane, it's the same molecule. Like the interaction between this molecule and this molecule is basically this entire part, right? This is the entire surface area that is allowed for interaction between this molecule and this molecule, this ID-ID interactions between this molecule and this molecule. However, if you look at this, right, like this will be a branch, this is a branch molecule, and hence this will be like closer towards the sphere. And as you can see, if it's branch, right, the surface area for interaction will be smaller, and hence the ID-ID interactions that can operate between molecules that are branched will usually be weaker because of the fact that the surface area for interaction is weaker. Okay, so I hope that makes sense. Basically, if the molecule has a larger surface area, then the surface area allowed for ID-ID interactions to act between the molecules will be stronger, and hence the ID-ID interactions will be stronger. Okay, so now on to the second type of intermolecular forces of attraction is the permanent dipole-induced dipole forces. So in the previous case, we talked about molecules that are non-polar. And the reason that it creates an dipole is because it's instantaneous, because electrons happen to congregate on one side. However, if the molecule is polar in the first place, then the separation of charges is actually permanent. And it's actually caused by the difference in electronegativities between the atoms. So again, like if we look at this example, right? So CH3F, there is a permanent dipole which is in this direction of the molecule. So there is a greater electron density on this side of the molecule as compared to this side of the molecule, and this separation of charges is permanent. It doesn't happen because of chance. It doesn't happen because electrons happen to congregate on one side at any instantaneous moment of time. This separation is really permanent because of the fact that the fluorine actually pulls the shared pair of electrons much closer towards itself as compared to carbon. Okay, and hence this actually has a permanent dipole. And when this molecule with a permanent dipole approaches another molecule that's non-polar, it will it would similarly induce a dipole moment in the other non-polar molecule. So for example, oxygen molecule, OO, it's not a polar molecule because of the fact that both atoms are oxygen. There's no difference in electronegativity between the two oxygens, hence it's non-polar. And the electron density is evenly distributed around the O2 molecule. However, on the other hand, water, right? Water, there's a difference in electronegativity between O and H, and hence the electrons that is shared between O and H is much closer towards oxygen as compared to hydrogen, and hence oxygen acquires a permanent delta minus and hydrogen acquires a permanent delta plus. And if you were to add up these two vectors, right, you will get a net dipole moment in this direction, and hence there will be delta minus here and a delta plus here. This is the permanent dipole of the water molecule. When this water molecule orientates like this in the direction of an oxygen molecule that is non-polar, it would cause this oxygen to rearrange its electron density to place more electrons on this side and less electrons on this side. So there is now an attraction between this created induced dipole delta plus with this delta minus on this on this water molecule. And this is known as a permanent dipole induced dipole interaction. And this force of attraction is expected to be stronger than the ID-ID forces of attraction because this is created by a permanent dipole, and this delta minus is expected to be larger than that created by an instantaneous dipole of a non-polar molecule. So the magnitude of this delta minus in the PD in a permanent dipole is larger than the delta minus created in an ID interactions. This is because this one is created by chance, but this one is a permanent separation. And hence PD-ID interactions is stronger than ID-ID interactions. The next type of intermolecular force of attraction is the PD-PD interaction. Okay, so we already mentioned that for polar molecules, difference in electronegativity generates permanent dipole moments, such as in the ICl molecule. Chlorine has a stronger electronegativity as compared to iodine. So in the ICl molecule, the chlorine actually pulls the shared pair of electrons closer towards itself, and there will be a partial minus charge that is on this chlorine atom, and there is a partial positive charge on this iodine atom. And when it approaches another ICl, which also has a permanent dipole, they will orientate themselves such that this delta minus is facing this delta plus, and there will be an attraction between this delta minus and this delta plus, and this is known as the PD-PD interactions. And of course, the PD-PD interactions will be stronger than the PD-ID interactions because both delta minus and delta plus is greater than in the case of PD-ID interactions. Okay, so I hope that makes sense. And one thing that just to point out is that although these dipoles are permanent, right, there is actually other electrons that other than these shared electrons in this molecule, and those electrons can still move about randomly, and they can also happen to congregate on one side at any given amount of time. So my point here is that for a molecule that has ID-ID interactions only, then it doesn't have PD-PD interactions. However, for a molecule that has PD-PD interactions, right, it would also have ID-ID interactions. All molecules that's covalent in nature always have ID-ID interactions. And the reason is because the remaining electrons that is not in the bond that creates the permanent dipole can have the same effect of the ID-ID type of interactions, because the remaining electrons can happen to congregate on any one side at one time, creating a delta minus and delta plus that's instantaneous, and that will add on to the PD-PD interactions. Okay, so molecules that have permanent dipole forces of interaction also have ID-ID interactions, but molecules that only have ID-ID interactions will not have PD-PD types of interaction. Okay, I hope that makes sense. Okay, so the last type of intermolecular forces of attraction is hydrogen bonding, which is the strongest type of intermolecular forces of attraction. And the prerequisite for hydrogen bonding is that you need a hydrogen to be covalently bonded to a very electronegative element such as fluorine, oxygen, or nitrogen. So for example, you need a H bonded to an F, you need a H bonded to an O, or you need a H bonded to an N. Okay, and the reason for this, right, is that fluorine is the most electronegative element in the whole periodic table, followed by oxygen, followed by nitrogen. And of course, all these bonds are going to be polar, right? Because like the hydrogen only has one proton and one electron. So the electronegativity of hydrogen is going to be very, very low. And hence, the electrons will be put very closely towards F, O, and N. Another way of saying it is that there is a very, very large difference in electronegativity between F and H, O and H, as well as N and H. And hence, the delta minus and the delta plus created when a H is bonded to either F, O, or N, right, it's the strongest type of PD-PD interaction, such that we actually give a special name to it called hydrogen bonding. Okay, so if you were to read here, the electronegative element pulls the electrons of the covalent bond so strongly towards itself that this hydrogen bond is essentially left with no electron density. So it's like the delta plus on the H is the strongest type in all the different types of PD-PD interactions. Okay, such that we give it a permanent called hydrogen bonding. The hydrogen atom essentially becomes a bare proton, very, very high delta plus charge. Okay, so when another very negative electronegative element such as fluorine, oxygen, or nitrogen with a lone pair of electrons approaches such as bare proton, significant attraction will occur between the lone pair of electrons and the bare proton. So basically what this means, this will create a very delta minus and delta plus such that this hydrogen is almost like a bare proton. And then when you have another molecule that's like fluorine, that is also very delta plus, this type of interactions between this delta minus on this fluorine and this delta plus, it's the strongest type of PD-PD interaction and is known as hydrogen bonding. So, and this is the reason why hydrogen bonding is the strongest among the four, because the magnitude of the delta plus and delta minus is the strongest among the four types of intermolecular forces of attraction that we have discussed so far. Okay, so this is hydrogen bonding. You have H bonded to O, thus creating a very large delta plus. This oxygen is very delta minus. So this strongest attraction of PD-PD type of interactions is called as hydrogen bonding. Another example, this is H bonded to an N. So this is very delta plus and this is very delta minus. And the attraction between this H and this N, it's called hydrogen bonding, which is the strongest type of PD-PD interactions. Okay, so anyway, just to basically, right, how do we decide whether a molecule is ID-ID interactions, PD-PD interactions, or hydrogen bonding? For hydrogen bonding, it's very simple. If the molecule has a H bonded to F, O, or N, it's almost certainly that the molecule will be hydrogen bonding, and it will be the strongest type of intermolecular forces of attraction, and it's likely that the molecule has the highest melting point or boiling point. To decide, if it's not hydrogen bonding, they have to decide whether it's PD-PD forces of attraction or ID-ID forces of attraction. In order to do so, first you have to use VSEPR theory to determine the shape. After you use VSEPR theory to determine the shape, you draw the bond vectors, then you add up the bond vectors to see whether the molecule has overall and dipole moment or not. If it doesn't have an overall dipole moment, then it will be ID-ID forces of attraction. If it has a permanent dipole, then it will be PD-PD forces type of attraction. Okay, so like where hydrogen bonding or not. Okay, this one is simple. Like whether you have H bonded to F or O or N. Okay, this one, if the answer is yes, it's hydrogen bonding. If it's no, it will not be hydrogen bonding. If it's not hydrogen bonding, then we have to see whether is it a polar molecule or not. Okay, if it's polar molecule, then if yes, then it would be PD-PD. If it's no, then it will be ID-ID. So this yes or no, you have to use VSEPR theory and then the shape of the molecule and the bond vectors to figure it out. Okay, I hope that makes sense. Okay, so a bit more on hydrogen bonding. The hydrogen bonding is the strongest intermolecular force of attraction. It's responsible for certain properties such as the dissolution of organic compounds such as alcohols and carboxylic acids in water. So we'll talk more about dissolution, but the fact that, for example, if you have a molecule such as this, which is an alcohol, right, and its interaction between this and water will be through hydrogen bonding, which is very strong. So we will say that the interactions between this alcohol and this water is through hydrogen bonding, which is the strongest among all 4 types of intermolecular force of attraction. The interactions are compatible, and that's the reason why it will be like water will be able to dissolve some organic compounds that can actually interact through hydrogen bonding with water. Okay, and the second thing is that the higher than expected boiling point of water and the open structure of ice. So we're talking about the open structure of ice later, but the higher than expected boiling point of water, as we know it, right, the boiling point of water is at 100 degrees Celsius, and the reason is because of the strong hydrogen bonding that exists between water. Now imagine, and we know that water is essential for life, right, in many aspects. We need to drink it. It's responsible for many metabolic processes. It's important for sweating, so on and so forth. It's important for acting as a solvent for many reactions to happen in our body. And the reason that it can happen is because water exists as a liquid at room temperature, right? Like for example, if you talk about another molecule, so water has an MR of 18. Okay, so the MR is like 18. If you look at another molecule such as methane, right, like CH4, the MR is actually 16. However, like I'm not 100% sure of the boiling point of methane, right? But I think it will be minus something degrees Celsius, and it's going to be a gas at room temperature. And of course, if it's a gas, right, it's not going to be useful for the human body. It's not going to be able to act as a liquid to dissolve compounds so that reactions can happen in it. It's not going to be able to be contained within our body such that we can use it as a coolant, so on and so forth. So it's important that water has hydrogen bonding so that even though it has a significantly small MR, it can still exist as a liquid that can serve the purpose that all life depend on. Okay? And it's also important for holding together chains of amino acids in proteins and bases in the double helical structure of DNA. So if you look at DNA, right, there are many amino acid residues, and the amino acid residues actually can interact through hydrogen bonding, and hence they are able to be contained within a double helical structure so that DNA can be packed closely within the nucleus of the cell. Okay? Okay, so the importance of hydrogen bonding in water and ice. So water is a liquid at room temperature and pressure, while other larger and heavier molecules such as CO2 are gases at room temperature and pressure. So if you look at the CO2, right, the MR is actually 44, which is much greater than the MR of 18 of water. And hence, the ID-ID interactions of CO2 is actually much stronger than that of water. However, because of the fact that water has hydrogen bonding, water is a liquid at room temperature, while carbon dioxide is a gas at room temperature and pressure. And we already said that it's important that water is a liquid so that it can support all the purposes it's required to sustain life. Okay, and also water is cohesive, and water molecules can stick to one another. The reason is because the attraction between one water molecule and another water molecule is through hydrogen bonding, which is very strong. And plants rely on this capillary effect to absorb and transport water out from the roots. So when the water like sucks up the water, right, the water molecule that is being sucked up will attract the water molecules below, and hence it will flow in a continuous stream that allows the water to continuously draw water up from the roots into the xylem. Okay, if there's no cohesive effect, right, then the stream of water will not be continuous, and it will be hard to draw water continuously up the xylem. And because of the fact that the hydrogen bonds are strong, a lot of energy is required to break it. So water has a very high specific heat capacity. Anyway, like for this term is probably not familiar to students that don't take physics, but heat capacity is basically the amount of energy required to change the temperature of unit mass of substance by unit temperature. Okay, basically, like if a molecule has a very high specific capacity, it means that it needs to take in a lot of heat before the temperature will be raised by, let's say, 1 degree Celsius. So because of hydrogen bonding, it has a very high specific heat capacity, meaning that it can take in significant amounts of heat before the temperature of water will raise by 1 degree Celsius. Okay, so it's used as a coolant in many biological and mechanical systems because of the fact that it's able to absorb a lot of heat before it will turn into, let's say, water vapor. Okay, like imagine if compared to another molecule that's very low specific capacity, it will not be able to absorb so much heat that before the temperature will rise very significantly. And of course, we cannot allow for temperatures in our body to rise significantly because it was going to affect all the cellular processes and all the metabolic processes, right? So we need basically a substance that can absorb a lot of heat before the temperature will rise so that we are able to maintain a significant body temperature that allows our body to function properly. Okay, and I'd just like to say that basically during all the metallic processes such as what do you call that? Respiration, you actually generate a lot of heat. So this heat has to be removed from your body, and the water is the one that absorbs the heat, and then like through sweating we will lose the heat. And it's because water can absorb a large amount of heat before they are lost that makes it an effective coolant. The last property is the anomalous expansion of water. So for most materials, right, as you cool down, the thing actually the substance actually starts to contract, and because the given amount of mass remains the same, right, and density, right, is equals to mass over volume, right? Okay, so as the temperature drops, right, the mass remains constant because we still have the same amount of substance. And then but the volume will actually drop because of the fact that the substance contracts. And if the volume contracts, right, it would mean that the density will actually increase. Okay, so generally for most substances, as the temperature drops, the density will increase. And this is true for water when you decrease the temperature from, let's say, like 90 degrees Celsius all the way to 4 degrees Celsius. In fact, the volume does drop because of the fact that the water contracts and the mass remains constant and the density will increase. However, from 4 degrees Celsius to 0 degrees Celsius, water behaves differently. And the reason is this, because like if you were to look at the structure of molecules in water at 4 degrees Celsius, or for any temperature between 4 to 100 degrees Celsius, it will be in this structure, whereby because of the fact that water interacts through hydrogen bonding, right, the intermolecular distance between one water molecule and another water molecule is actually very short. And as it starts to contract, it will become shorter and shorter. However, right, when from 4 degrees Celsius to 0 degrees Celsius, right, water needs to start turning into ice. And we all learn from kinetic particle theory, right, that in the solid state, right, the particles must actually arrange themselves to be in the fixed position in the lattice structure. And hence, when you go from 4 degrees Celsius to 0 degrees Celsius, right, it needs to start going to the correct, these are the correct lattice positions. It needs to go to these correct lattice positions that will be characteristic of the ice solid configuration. And hence, from 4 degrees Celsius to 0 degrees Celsius, instead of actually contracting, it actually expands to allow the water molecules to go to the correct lattice positions. Okay, so since it actually expands to go to the correct lattice positions, and the volume, as the volume increases from 4 degrees Celsius to 0 degrees Celsius, the density will actually drop. And as a result, right, the density of water at 0 degrees Celsius is actually is lower than the density of water at 4 degrees Celsius. And the result of this is that, right, since the density of water at 4 degrees Celsius is actually higher, right, water at 4 degrees Celsius will actually sink, while water at 0 degrees Celsius will actually float. And thus, ice actually floats on water, okay, because of the fact that ice has a lower density than water. And this is important because during winter times, as the ice floats on water, the water will be below, and the ice will actually act as an insulator to prevent the water below from losing more heat. And therefore, right, in the ocean, like this will be the ice, and then like the water below will not freeze because of the fact that this is like at 4 degrees Celsius, while this is lower than 0 degrees Celsius. Okay, and because obviously if the entire pond or the river freezes from the bottom up, right, all the marine and the aquatic creatures will be killed. They'll be frozen to death. But because of this anomalous expansion of water that allows ice to float on water, therefore marine creatures can stay alive during the cold winters. Okay, so the last part of this molecule is a bit unrelated to intermolecular forces of attraction, but I'm just going to put it in as we define various radii now that we are talking about intermolecular forces of attraction. So ionic radius is defined as the radius of the ion. So for example, if we look at the NaCl molecule, the ionic radius of Na plus is basically the distance between the nucleus and the valence shell. Whereas for the Cl minus, it's also between the nucleus and the valence shell. The covalent radius is defined as half the distance between two atoms of the same element held together by a covalent bond. So for example, if we look at the Cl2 molecule, it's half the distance between the nucleus and the shared pair. Sorry, it's the distance between the nucleus and the shared pair of electrons, or basically formally half the distance between nucleus to nucleus. Oops. The van der Waals radius is defined as half the distance between two non-bonded atoms. So it's important here that it's non-bonded of the same element on their closest possible approach. So for example, if we look at two argon atoms, these two argon atoms are non-bonded because like argon is a noble gas that has already a full octet configuration or full noble gas configuration, so it doesn't bond. So when they actually approach each other, right, they actually are non-bonded because they're not bonded to each other. And half the distance between nucleus to nucleus will be called the van der Waals radius. And I would just like to say that basically the van der Waals radius will always be larger than the covalent radius because of the fact that the covalent radius is the attraction between the nucleus, which it's made up of protons, which is like full charges, right, and shared pair of electrons, which is full minus. So like this magnitude of charges is like plus and minuses, but the attraction between these two atoms is actually through van der Waals force of attraction, which is due to delta plus and delta minus. And we really discussed that the magnitude of these charges is much, much smaller than full plus and full minus. So since this attraction is weaker, the distance between these two atoms will be longer, will be further as compared to between atoms that are covalently bonded. Metallic radius finally is defined as half the distance between two adjacent metal ions in the metallic lattice. So in the metallic lattice, for example, aluminium, these are the Al3 plus cations, and then there are C of delocalized electrons. And then half the distance between two adjacent metal ions, this will be known as the metallic radii. Okay, so basically like, I guess the main highlight of this defining various radii is because I want to highlight the importance that the van der Waals radius is actually much longer as compared to the covalent radius because of the fact that the van der Waals forces of attraction is much weaker than that of a covalent bond. Alright, so basically this sums up these two learning outcomes H and I, and I hope that now you're able to describe the forces of attraction in terms of intermolecular forces based on permanent dipole and induced dipoles, as well as in hydrogen bonding, and also be able to outline the importance of hydrogen bonding to the physical properties of substances, including ice and water. Okay, if you have any comments and questions, just drop it in the comment section and I'll be more than happy to answer them. If you like the lesson, just hit the like and subscribe button, and I'll see you for the next episode where we look at a few A-level questions that test on these two learning outcomes. So thanks for tuning in and see you once again.